Okay, today we're going to talk about the boundary layer equations. We've discussed some fundamentals of viscous flow. And now we're going to look at some equations, and next time we'll look at some ways we can solve these equations. So first off, let's just go to the 2D Navier-Stokes equations. We've eliminated the time dependency. We've also eliminated the normal shear stresses, but those are generally negligible. So this is just the 2D Navier-Stokes equation. And our goal here is to try to specialize these equations for the case of a boundary layer. So it may be in some terms that are important in the general flow field that are not as important in the boundary layer. In other words, we want to try to identify which of these terms are much smaller than the others within a boundary layer. We're also going to make the approximation that here's, say, for example, an airfoil surface, that we can consider the x coordinate to curve with the airfoil while the y-axis is always normal. So our coordinate system does change. It's not perfectly Cartesian anymore, but we're going to make that approximation. This is pretty analogous to the approximation we would make for, say, doing Newtonian mechanics on the Earth, where we don't account for the curvature of the Earth. So locally, if I'm doing, I'm calculating the trajectory of a football or something, I wouldn't account for the fact that the ground is curved, even though as I keep going further and further, right, there's some curvature. And that's just because the height I'm looking at is very small compared to the curvature. The same kind of approximation is applied here in the boundary layer, that these are very thin relative to the curvature. If the curvature is significant, for aerodynamic shapes, typically that would only be during the leading edge. So very small portion, there is a curvature term we can add. But in general, if there's areas of really high curvature, anywhere after the favorable pressure gradient, we're going to have separation. And so we won't have a boundary layer anyway. So that term is rarely important. Okay, so again, our goal is to try to simplify these equations for the boundary layer. What we know in the boundary layer is that our main assumption is that the height of the boundary layer, which we haven't really defined, but there's not necessarily an edge, but this height delta is much smaller than the length or the x distance that we move along the boundary layer. Okay, so basically the same assumption we've already made. If that's the case, then we can look at just this continuity equation, and in every case we're going to look at just orders of magnitude. How do things change in relative magnitude? So density, magnitude is going to be the same. U, what's the magnitude of U? Well, we could use our edge velocity, for example. So if I just take this equation here, I could say from a scaling point of view, U is going to be proportional to my edge velocity. As that increases, I expect my U component in the boundary layer to also increase. And X is proportional to the length. And I know that term has to be balanced by this one. And now again, I'm canceling out the densities. They're going to be relatively similar in magnitude. So I've got V, and scale of Y is delta. So this tells me that V is going to be proportional to, again, this is just orders of magnitude, my edge velocity times delta over L. So this is the first thing we notice from this boundary layer analysis, is that because we're assuming delta over L is a really small quantity, right? Delta is much smaller than L, then my vertical velocities on the boundary layer must be much smaller than my horizontal velocities. Okay, so that's the first assumption, and we're going to continue that. I'm actually not going to go through all the equations here in the video because they're in the book, but this is the process we use. We take that assumption and now we plug that in for V. We use VE for the edge velocity, or sorry, for U, just as before. And we just, again, look at which terms are bigger or are much smaller than some of the other terms. One of the things we'll find as we do that is that our assumption, as we look at these viscous terms, we'll see that delta over L is going to be proportional to 1 over, I believe, the square root of the Reynolds number, or perhaps the Reynolds number directly. Yeah, I can't recall. Either it's the Reynolds number or the square root of the Reynolds number, but in either case, we can see that to have this assumption here that delta is very small is analogous to assuming that the Reynolds number is large. Okay, so that's the consistency there. So go through that again, check out the book if you're interested in doing that in more detail, but the basic concept I've already described. And this is what happens. The first term, of course, we can't leave anything out. There's only two terms here, so we just thought they'd be balanced. In this equation, everything is of the same magnitude, except for this term is much, much smaller than this one, so we can neglect it. And actually, this is a little bit confusing in the slides because I wrote this in the incompressible form, and this is the compressible. But anyway, in the book, I do it in the compressible case all the way through. In the last equation, every term ends up being much smaller than just this one. So this is all that we have left. Okay. Well, that leads us to another interesting insight. If we think about physically what this means that the pressure does not change in the normal direction. So in other words, and I will greatly exaggerate my boundary layer. This is my boundary layer. That means that the pressure that I compute here in my inviscid solution just outside the boundary layer is the same as the pressure on the surface, that just transmits through the boundary layer without any change in the y direction. That's actually very fortunate. That means that the pressure field that we computed from our inviscid solution, say in our last section of the panel code, and we integrated it to get forces and things, that actually is going to be a very good approximation because that pressure outside the boundary layer does not change against the surface. So even though we didn't actually compute the pressure on the surface, it's a very good approximation for the pressure that would be on the surface. And of course, the boundary layer is much thinner than this. It's not so much a geometry change that we're worried about. It's more so pressure changing, which it does not in this boundary layer approximation. That's really great. It also will simplify our equation because this term here is now not a partial derivative. It's just a total derivative because pressure is no longer a function of x and y. It's just only a function of x. So there's no longer a partial derivative. In fact, that'll allow us to simplify the equations a bit. So again, kind of looking at the same principle. Here again is my airfoil. Here's my boundary layer. And if I want to know the pressure right here, we said it's the same as the pressure just outside. So I could, right, if I take this point and this point, they're all going to match up. So if I want to know how pressure changes in x on the airfoil, I want to know that dp dx term, right? I could look at how dp dx changes just outside the boundary layer. It should change in the same way. That's very nice because outside the boundary layer, it's inviscid. So we could just use the Euler equation. All the other terms are gone. So I just would have minus rho edge v edge times dv edge dx. Right, that's the Euler equation. So those are all inputs. Those are solutions or inputs from my inviscid solution. So now I can plug this in. I can plug this in right here into my boundary layer equations. And that gives me this final result here, right, which I have now still the continuity equation, d rho v dx plus d rho v dy equals 0. And then I've got rho times u du dx plus v du dy equals, and now I substitute in this term in for the pressure. I get rho edge v edge dve dx, actually just rho, plus d by dy of mu times du dx. Okay, so this is actually, maybe this should be rho edge. So this is my boundary layer equations. This is the differential form. And if it's incompressible, a lot of this is going to simplify greatly. So if it's incompressible, for example, these densities cancel out. This cancels out. This one just becomes nu. And then this derivative can move over here because mu is not a function of temperature for the incompressible case. So it's a constant. And this just becomes a second derivative of u. So we can make all of those simplifications. Actually, let me just write that out. So the incompressible one is going to be dx plus dv dy 0. And then this one is u du dx plus v du dy equals ve dve dx plus nu. Sorry, that's nu. That's the kinematic viscosity. Second derivative u with respect to, this should have been a y. Yeah, I think I do that right now. Yeah, that's a y. Sorry, let's do it in the same color. So this is the differential form of our boundary layer equations. And the third equation went away, right? That was that pressure term that we used to simplify this one. So we've taken our Navier-Stokes equations. We've simplified it into this form now, which is easier to use. And the reason for that, well, first of all, there are less terms here, so that's nice. But the main reason why it's easier is that the original equation is what we'd call an elliptic PDE. So if I go back to the original one, an elliptic PDE, at least in 2 dimensions here, is going to have second derivatives in x and y. Okay, but this is called a parabolic PDE because it only has second derivatives in one of the dimensions, in this case y. So let me just erase this for now. We're only going to use the incompressible one now. So here's the incompressible one. It's easier to solve, but it also really changes the types of boundary conditions I need. So for an elliptic PDE, so this is the elliptic case, and this is my domain, I need to provide boundary conditions. These are my boundary conditions on all the sides, right? It doesn't have to be a rectangle, it could be a circle, bullet shaped, whatever, but around the entire perimeter of my domain, I need to provide some sort of boundary condition. And then those boundary conditions are fed in, right? And this is what we typically do in CFD, right? In the parabolic case, I don't need boundary conditions like that. So in the parabolic case, I only need boundary conditions on just one side, and I can march that forward in space or in time, in this case in space. And that kind of makes sense physically with what we're doing here, which is a boundary layer, meaning I can set an initial condition on one side of my boundary layer, and I can propagate that forward, solving forward. I don't have to go from all different directions here, so I can just kind of solve forward in time. And that's a much easier thing to do. That's also like the wave equation is a parabolic PDE, right? I just initial condition, I march forward in time. Okay, so we're also going to look at an integral form of the boundary layer equations. But before we do that, we need to define a couple of terms. We've used the phrase height of a boundary layer. We've never really defined that, right? There's not a hard edge where things suddenly change. So we need some way to quantify the height of our boundary layer. And there are 2 quantities that are most useful. First one is called the displacement thickness, and it is given by the symbol delta star. So actually is going to correspond to this height here. I'm going to call it delta star. So physically what it means is this is the real flow, real viscous flow, right? There's a boundary layer and there is a velocity deficit. So if I looked at the mass flow rate deficit, that's this area in red here. Okay, that's the amount of mass flow that I'm losing from the presence of viscosity. Now I could think of a fictitious flow that was inviscid, everywhere is constant at the edge, but I just grow the wall by exactly this area here in red, right? So in other words, I make my body bigger so that this mass flow rate is exactly equal to this. So in other words, my displacement thickness is the height I would need to displace or increase the thickness of my body to have the equivalent mass flow rate, right? So this is I want the same mass flow rate in both cases. So on the left, my mass flow rate, I just have to write it as an integral. It's completely general. So let's say height, I'm going to integrate up to some height h. And it's going to just be rho VA, right? So rho U dy in this case. That's my mass flow rate. And I just have to integrate that in a general way. On the case on the right, I could write it this way just for convenience. It's equal to, it's an integral, but it's an easy integral, right? Because everything's constant, but I'm going to keep it as an integral for now because it just makes things easier for the derivation. Rho edge V edge dy, right? All of those things those are all constant. And I'm integrated from 0 to h just for convenience. So I start from here to there. But now I got to subtract out this part that doesn't contribute, right? That's my wall. And so that's going to be, I could write this also as an integral, but I'm going to skip that because just again, this just makes the derivation easier. Okay, so like that. All right, so this first term, I could have wrote it as rho edge v edge times h, right? Or this whole thing is just rho edge v edge times h minus delta, this height here, okay? But leaving it like this will make things simpler. So now I just take these two things, I equate them, and I solve for delta star. That's why I wanted to leave this out so I could solve for delta star more easily. And I wanted to leave these under the integral so I can combine them. Here the math is straightforward. I'm just going to skip to the end though. Delta star now is the integral from 0 to h of 1 minus rho u over rho edge v edge dy. Okay, so this is my definition. And actually the other thing that we do, because h was just this arbitrary height that we defined, right? We just integrate to some point. We don't really know where that is, but we notice that if we go far enough, right, as h becomes larger and larger, this term here, rho u, should approach the denominator, right? By definition, I'm approaching that value. So this approaches 1, so eventually this goes to 0. And so I can go as far as I want, and anything beyond that point will contribute nothing from a point of view of the boundary layer. So by definition, we just take this to infinity because it goes to 0 at some point. So this is the definition of the displacement thickness. Okay, and again, the infinity just means that at some point this goes to 0. So that's, continuing further doesn't mean anything. Physically, again, where this is kind of the idea that it defines how big we'd have to make our body to get the equivalent mass flow rate. And that's a useful concept because it can help us create this idea of what's called the effective body. So in other words, let's say I solved my inviscid solution over this actual body. This is the shape of my body that I solved for. I computed the inviscid solution, so I get the pressures, I get the edge velocity. With that inviscid solution, I can now go and compute my displacement thickness everywhere. And that's like, I could then increase the thickness of my body everywhere according to delta star. And that's now what the inviscid flow solution, to be more accurate, is really seeing. It's an inviscid flow around a body that's actually a little bit thicker because of viscosity is decreasing some of that mass flow. So if I want to do this well, then I should make the body bigger and then go back to my inviscid solution and resolve it now with this body that's a little bit bigger because of that displacement from viscosity. So we could do that, we could iterate, although in practice, we'll usually do something a little bit different because doing this way is more complicated. It's a little less efficient because what we have to do, if we change the geometry of the body, we have to repanel everything, right? We have to rediscretize, we have to resolve all our influence coefficients. And in 2D, that's not a big deal, but for 3D geometries, that can be problematic, right? And then we have to think about maybe intersections as these bodies, if I've got a wing body junction, and there are a lot of little details that make this a little more complicated. So we'd actually not like to change our geometry. So instead, we're going to change our boundary condition. And I won't fully derive this because it's in the book, but I want to explain the concept again, which is this. In the inviscid solution, when we did our panel code, we used a boundary condition, which is that at the surface, the normal velocity is 0. And that's how we solved it, right? But really what we're doing, if we think about it, is that I have my geometry and I've got this boundary layer, again, greatly exaggerated. And effectively, we're solving for right here, just outside the boundary layer where it's inviscid. And in that case, the normal velocity is not actually 0. Right? So we could do one of two things. We could either make the body bigger and then still use the same boundary condition, right? Because now we made a thicker body. We basically treated it like this solid wall. So that all works. Or we're going to leave the body as is, right? So we're going to solve it here, just normal, but we're going to use the velocity from the boundary layer, right? We're going to assume the boundary layer is thin. And the boundary layer, at the top of the boundary layer, the normal velocity is not actually 0. Okay, so I derived this in the book, but the result is following 1 over rho edge d by dx of rho edge v edge delta star, or in the incompressible case, which we'll typically do, these would cancel. All right, so that just gives me a new boundary condition. Once I've solved delta star, I'm computing the effective normal velocity, which is no longer 0 because there is some vertical velocity, right, as we've seen in the boundary layer. Go back to these equations, right? There's some vertical velocity. As we've discussed, it's small, but it is not 0, okay? So this gives us a procedure that can be used in a coupled inviscid viscous or a coupled inviscid panel or potential flow solution with the viscous boundary layer method. First, right, we analyze, well, let me just simplify this. Let's just say, do the inviscid solution. And that's going to give us our edge velocity and pressure and so on, right? Now that we have the edge velocity, we can solve the boundary layer equations, right? And that's going to give us delta star. And there it is. There's a delta star over there. Okay, so now number 3, we're going to do the inviscid solution with the normal velocity not equal to 0 at this time. Right, we're going to use this new modified boundary condition. And then we may need to go back and repeat again. Okay, or more in a better way, we don't have to do this fixed point iteration. We could couple these. We could solve the residuals in the same way, like a Newton method or something. And that's typically what a panel code does that has an integrated boundary layer method with it, a viscous solution with it. Okay, so we've defined displacement thickness, and this was based off a mass flow deficit. Well, the other way we could define a height is based off a momentum flow deficit. So same idea. The symbol, though, is theta. Okay, same idea, derived in the text, so I'm not going to do it, but just write the answer here. Okay, it's an integral, also rho u, rho edge v edge, and again, the rho's would cancel for incompressible. 1 minus u v edge dy. Okay, so it is the similar concept, but instead of using the mass flow rate, we look at the momentum flow rate, and we equate them between these two scenarios. And this is very useful because this momentum deficit is what we're measuring, and that is directly related to drag, right? As we've discussed, if there was no momentum deficit, if the velocity profile in front and behind, say my geometry, were just the same, that would mean there was no drag, right? All the disturbances were gone. But we have this momentum deficit, there's some velocity that's left behind, and that is drag, right? We've extracted some energy from the flow. So theta is useful for predicting drag. And in fact, for a flat plate, simple case here, right? If this is x, then the drag per unit depth, right, at any location x is just rho e ve times theta. Oh, sorry, rho v squared. Theta as a function of x. So theta is growing, right? So theta is this height. So I just calculate theta and any given x point, that gives me my local drag at that point. And we'll see later that it'll also be useful for more complex cases like an airfoil, not such a simple formula, but that we should be able to predict drag, or we would hope to be able to predict drag based on momentum thickness. All right. Well, there are the boundary layer equations that we've described have some analytic solutions. They're pretty limited. They're over very simple geometry, so we're not really interested in them in this class. We're going to look at numerical solutions that we can use for arbitrary geometries within the assumptions of boundary layer theory. But one useful analytic solution is for a flat plate, because that's a simple case and it's a basis of many comparisons. And I'll just write down a few of these. So for a flat plate, we can actually solve it. It looks something like as follows. Okay, theta, this is the momentum thickness, 0.664 x squared Reynolds number. And these actually can be solved for compressible cases too, but it's not as it still requires a numerical solution, I think. There's not an analytic form. And then the skin friction coefficient is as follows, 664 over Reynolds number. And by the way, this is why this expression here, if we look at it, you'll note that the skin friction coefficient is highest when x is small, which is why, like say for a hobby airplane, you put a lot of the smoothing, let's say we put tape or whatever, or a smoothing agent, we put it towards the leading edge. Or if we were sanding, we put more focus towards the leading edge because that's where the skin friction coefficient is going to be highest. We get the most bang for our buck there, especially if we're adding weight through things like tape. We mainly do it towards leading edge. And then big CF, which is a drag coefficient, right? It's the integral, is equal to 1.328 over square root of Reynolds number based on length. So the difference of those, if you remember that the skin friction coefficient is just the shear stress. It's a normalized shear stress. So we divide by the dynamic pressure. Whereas capital CF is called the skin friction drag coefficient, right? This one is a shear stress. This one is a drag. So in other words, capital CF is the integral of the shear stress along the body, and then we normalize by Q infinity and the total length that we integrate across. So if we plug all those things in, this is just equal to the integral of the local skin friction coefficient divided by L. And so this is drag per unit length normalized. So this is the drag coefficient, this is a shear stress. For the turbulent case, there's not an analytic solution. There are empirical formulas. There are not one, right? Because empirical, there are many such formulas. The book shows one such formula you can take a look at. You'll note that these things grow faster, right? These displacement thickness, momentum thickness, the boundary layer height grows faster as we would expect. But I won't copy those down right here. Okay, so we looked at the differential form of our equations. We're also interested in an integral form, just like we were for the general flow solutions. I do also derive this in the text. It's rather lengthy, so I won't do it here. I'll just write the result, which is 1/2 times CF, that's a lowercase cf, equals d theta dx, that's our momentum thickness, plus dve dx, that's our velocity gradient, times theta over ve times h plus 2 minus Mach number squared, the edge Mach number squared. And again, for us, incompressible, that means by definition, the Mach number is 0 for incompressible flow, so that one goes away. Well, we have one new term here, that's h. H is called the shape factor, and it's defined as just a simple ratio. It's not really a new variable per se. It's just a ratio of these two heights that we've seen already, because these two actually grow at different rates for the most part. For a flat plate, they grow at a similar rate, so this actually ends up being a constant. But for a general body, they often grow at a different rate. So H can change along the boundary layer. The reason we call it H, and actually I'm not sure if this is the reason why, but it's convenient, is that it's an indication of the health, so hence the H of the boundary layer. Just to give you an example of this, let's look at this figure. This is from X-Foil. This is a popular coupled panel code with an integrated boundary layer. Very useful tool here to analyze an airfoil. And what we're seeing here first in the upper left is the pressure coefficient. We've seen these before, but what's different here is that you can see actually two sets of curves. Let me just zoom in and just focus on this for now. There's a dashed line and there's a solid line. As you might expect, if you look at it for a little bit, the dashed line is the inviscid solution, right? And the solid line is with the coupled viscous solution as well. So it's modified the pressure a little bit. You'll notice though the changes aren't too drastic. The boundary layer is actually plotted here, and you'll see that it's extremely tiny, right? You can only really notice it here towards the trailing edge. Okay, so the viscous solution has modified the boundary layer a little bit, but what we're interested in, I'm going to show you H. So this is a plot of H along the boundary layer. So ignore this back part, but we're going from 0 to 1. which is from the leading edge to the trailing edge. And we're looking at two surfaces. This is over the upper surface and then over the lower surface. So over the lower surface, not too much is happening. Over the upper surface, this is increasing rapidly and then it drops. So you might ask yourself, well, what's happening here? Well, right here is where we transition from the laminar flow to the turbulent flow. So it turns out that H, for a flat plate, H of, let me just write this down. There we go. For a flat plate, this is not for in general, this is not this case, but just to give you some idea. For a flat plate, H less than 2.59 means that the pressure gradient is negative. Or in other words, it's a favorable pressure gradient. And if it's greater than 2.59, that means we have a adverse pressure gradient. So we can expect that as H gets bigger, right, in a general scenario, that pressure gradient is more adverse and we're likely to transition or to separate. And in fact, typical rule of thumb is that for a flat plate, it's a simple geometry, but for a more typical geometry, that greater than 2.2 is an indication of, say, transition or separation. Somewhere around there. That's just a rule of thumb, right? As it gets larger. So in this case, we can see what's happening. It's starting out relatively flat, and then it grows, and now it's getting big. So we're going to transition to turbulent flow, and now that we're bringing in that momentum, that extra energy, H goes way down again, and then it's starting to grow again towards the trailing edge. We can also see where separation occurs by looking at the skin friction coefficient. Recall that skin friction coefficient is just a normalized shear stress, and shear stress is mu times du dy at the wall, right? Because CF is related to tau at the wall. So when this goes to 0, right? Remember, if we plot our boundary layer profile, this is y and this is u, that at separation, that slope becomes 0. So that indicates separation. So here, where our skin friction coefficient is 0, that indicates that initial small amount of separation and transition here to a turbulent flow, and then increase again in skin friction coefficient. And again, we notice here this large CF at the beginning, as we saw in the Blazia solution, that because it was divided by the Reynolds number on the bottom, square root of Reynolds number as a function of x. So there's a square root of x on the bottom. So it becomes really large with small x. So there's a very high skin friction coefficient towards the nose, comes down, we separate, goes back up again here in turbulent flow. Okay, so that's it for today. We've kind of discussed two equations, both which will be useful, a differential form and an integral form of our boundary layer equations. And we've introduced two heights that we're going to make use of: displacement thickness, which is related to the mass flow rate, and momentum thickness, which is related to the momentum flow rate. And then H here is just the ratio. It's indicative of health. And so next time we're going to look at how we can actually solve these boundary layer equations for a laminar case, and the time after that we'll look at a turbulent case. So we're going to look at numerical solutions for general shapes.